Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 asks, what is the percentage of iron in an iron ore, which is 60% by mass of iron 3 oxide? Okay, so let's write down what we know. We know that 60% of iron is in iron 3 oxide. So let's write down the formula for iron 3 oxide, just so that we can see how many iron atoms are in iron 3 oxide. So we know that the iron has an oxidation state of 3, and we know that since this is not a peroxide, then our oxygen has an oxidation state of -2. So that makes our chemical formula Fe2O3. Okay, so now that we know the chemical formula of iron 3 oxide, let's find out its molar mass. So the molar mass of iron 3 oxide will just be 2 times the molar mass of iron plus 3 times the molar mass of oxygen. So these are values you can just find on your periodic table, and the molar mass of iron is 55.8 grams per mole, and the molar mass of oxygen is around 16 grams per mole. So now if we sum these values up, we end up getting a molar mass of 159.6 grams per mole. Okay, so now that we know the molar mass of iron 3 oxide, let's assume we have 1 mole of sample. Just so that we can compare everything in grams. So we know that 60% of the iron 3 oxide contains iron. So if we let X equal the mass of iron, then we can try to find out the mass in this sample. So we know 60% of it is the iron, so we just need to say 0.6 X is equal to 159.6 grams. So this is the total molar mass of iron 3 oxide. And now we just need to solve for X. So if we divide both sides by 0.6, we get X is equal to 266 grams. Okay, so this is step 1. And now step 2. We know that in iron 3 oxide, there are 2 iron atoms. So if we think about the molar mass of just iron, it is 55.8 grams per mole. So if we multiply this value by 2, we can get the mass of iron. So 55.8 times 2 gives us 111.6 grams. So we know the mass of iron ore, which is 206 grams, and now we also know the mass of iron. So now, step 3 is to find the percentage of iron in iron ore. So we take the mass of our iron, which is 111.6 grams, and we divide that by the mass of iron ore, which is 266 grams. And if you multiply this by 100, we can get the percentage, which is 41.95%. Okay, so now let's see what the junior tutor said. This problem states that an iron ore is 60% by mass of iron 3 oxide, which has a chemical formula of Fe2O3. To solve this problem, we set the following variables. X is the mass of iron ore, and Y is the molar mass of iron 3 oxide. So they set Y equals to X, Y equals to 60% X. So it's basically the same as our first step. And then they calculated the molar mass of iron 3 oxide. So they also got 159.68. And then they got the mass of iron ore by multiplying or dividing your molar mass of iron 3 oxide by 0.6. So they also got 266 grams of iron ore. Okay, so then they found the mass of iron by multiplying the molar mass of iron by 2, and then they divided the values to also get around 41.9% of iron. So this solution is correct. Okay, so question number 2 is to calculate the molar mass of sodium chloride, NaCl, from the periodic table. We know that sodium has a molar mass of 22.9 and chlorine has a molar mass of 35.45. So to calculate for the molar mass of NaCl, we just need to add those values together. So the molar mass of sodium plus the molar mass of chlorine. So these were given in the question. Sodium's molar mass is 22.99 grams per mole. And chlorine's molar mass is 35.45 grams per mole. So if we added these values together, you end up getting a total sodium chloride molar mass of 58.44 grams per mole. So therefore, this is option B in our question. Okay, so the junior tutor said that the molar mass of a compound is the sum of the individual atomic masses of the elements comprising the compound. They have the molar mass of NaCl is equal to the sum of the molar masses of sodium and chlorine, and they also got 58.44. So this solution is correct. Okay, so question number 3 just asks, what is the molar mass of diatomic oxygen? Okay, so this is fairly easy as well. We just need to look at our periodic table and find out the molar mass of a singular oxygen atom. So if we look at the periodic table, we'll find that its molar mass is around 16 grams per mole. So now when finding the molar mass of O2, all we need to do is multiply that value by 2. So 2 times 16 grams per mole gives us 32 grams per mole. And this is the molar mass of O2, which is the air that we breathe, actually. And the junior tutor said that the molar mass of a molecule or compound can be calculated by adding the standard atomic masses in grams per mole of the constituent atoms. Hence, the molar mass of O2 is 31.998 grams per mole. And then they just showed their work. So this solution is correct. Okay, so moving on to question number 4, which just asks, define nonpolar covalent bonds. Okay, so let me just move this over. Nonpolar covalent bonds. This is when two atoms have equal or similar electronegativity values. Okay, so let me just underline it. So typically, in nonpolar covalent bonds, the difference in electronegativity between the two atoms, it ranges from around 0 to like 0.4. Okay, so some examples of nonpolar covalent bonds would be like diatomic gases such as N2 or O2. So obviously, since you have two of the same atom that are bonded together, they will have the same electronegativity. So, obviously they just have a difference in electronegativity of just 0. And another common nonpolar covalent bond would be like the carbon-hydrogen bond. So let's just show up here how we can calculate the difference in electronegativity between carbon and hydrogen. Let's just search electronegativity values. See all the different values of these elements. So carbon has an electronegativity value of 2.5, and hydrogen has an electronegativity value of 2.1. So 2.5 minus 2.1 is equal to 0.4. So this lies within this range of 0 to 0.4. So this makes our carbon and hydrogen bond nonpolar. So now we can compare nonpolar covalent bonds with polar covalent bonds. And as you can guess, this is when you have two atoms that have dissimilar electronegativity values. Leading to a dipole moment. Typically, its electronegativity ranges as well. Greater than 0.5, but less than around 1.69. Okay, so let's look at some examples of polar covalent bonds. A common one is the hydrogen-oxygen bond. So again, let's try to calculate its difference in electronegativity. Oxygen's electronegativity is 3.5, and hydrogen's is only 2.1. So this makes this difference in electronegativity equal to 1.4, which lies within this range, making the OH bond polar covalent. Another example of a polar covalent bond would be like phosphorus and fluorine, or like carbon and oxygen. These are examples of polar covalent bonds. So you can distinguish whether or not something's polar covalent because covalent bonds is when you have the sharing of electrons between two nonmetals. And that's why this difference in electronegativity just kind of helps us distinguish whether or not a bond is nonpolar or polar, because we can also have something called an ionic bond. Which is between a metal and a nonmetal. So the minute you see that a metal is involved in the bonding, That's how you know you have an ionic bond. So even if you calculated its difference in electronegativity to be around like 1.68, we know that it won't be polar covalent because it contains a metal. But typically, its difference in electronegativity is greater than 1.7. So let's look at an example for ionic bonds, like potassium fluorine. Potassium is a metal, and fluorine is a nonmetal. And if we were to look up their electronegativity values, fluorine has an electronegativity of 4, and potassium's is only 0.8. So we get a really high electronegativity difference of around 3.2, making this potassium fluorine bond ionic. Okay, so now let's see what the junior tutor said. When the electrons of an atom attract the electrons of another atom, making this chemical attraction, it is called a chemical bond. It has two types, which are ionic bonds and covalent bonds. Ionic bonding is where the electron of an atom is donated to another atom, making an exchange and forming a bond. Ions are formed. We have positively charged ions, which are cations, and negatively charged ions, which are anions. Covalent bonding is where the electrons of the both atoms are shared between one another, forming a bond. It also has two types, which are polar covalent bonds and nonpolar covalent bonds. A type of covalent bond, a polar bond, is where one atom gains a partially positive charge while the other gains a partial negative charge, having unequal sharing. On the other hand, a nonpolar bond is where there is no charge separation, both having equal sharing. Therefore, and then I guess they summed it up. Yep, so this solution is correct. I'm just going to put the difference in electronegativity value that might help distinguish between polar and nonpolar covalent bonds. Okay, so I just put some examples of what these differences in electronegativities might be. Maybe I should define En. Okay, so this solution is correct. Okay, so question number 5. What is vaporization? Vaporization is when you have a liquid converted to gas. Also known as like a phase change. So when we reach temperatures that are higher than a compound's boiling point, then this is when vaporization will occur. So for example, let's say we had liquid water and we boiled it at temperatures greater than 100 degrees Celsius. Then, I didn't even show the phase. If we had liquid water that was boiled, so this triangle shows that heat was applied at temperatures greater than 100 degrees Celsius, which is the boiling point of water, then a phase change occurs and the water is converted to gas, and this is called vaporization. So the junior tutor said that vaporization is one of the phase changes of matter wherein the liquid state of the substance is converted into its gas phase. Boiling is the term for the process if the conditions allow the formation of vapor bubbles within a liquid. So this is when you heat up a pot of water on the stove and you start to see the bubbles form, then you know that your water is boiling. Moreover, heat must be supplied in order to successfully evaporate a substance. This is often called the heat of vaporization, which refers to the amount of energy needed to turn 1 gram of a liquid into vapor without a rise in the temperature of the liquid. Okay, so the solution is correct. Okay, question number 6. How many kilobytes are in 1 gigabyte? Kilobytes in 1 gigabyte. In 1 gigabyte, there are 1,000,000 kilobytes in 1 gigabyte. Okay, so we can write it like this, or we can write it in scientific notation, where it's 1 times 10 to the 6 kilobytes. And we know this because of the prefixes kilo and giga. So we can also change our base, which is bytes. So let me call this like your base. And then these are the prefixes. And we can change our base to anything we want. So let's say we had kilometers. Well, I'll write it over here. even though we don't technically use the term gigameter, it can still technically exist. So let's say we had 1 gigameter. This would also be equal to 1 times 10 to the 6 kilometers. And the reason for this is because of these prefixes that can help us convert from different units, whatever is easier. So the reason why gigameter isn't really used for our purposes like traveling is because like cars don't usually travel like 1,000,000 kilometers to go somewhere. But if we were to use these prefixes to describe bytes, which obviously you can have a lot of, and we always talk about having a lot of these bytes, then this is when you would use these prefixes. And the junior tutor said that there are 1 times 10 to the 6 kilobytes in 1 gigabyte. And then they showed their work. So this solution is correct. Okay, question number 7. How many valence electrons does a carbon atom have? So first, let's look up carbon on the periodic table. Let's just find a normal periodic table. Okay, so carbon is found here. And we can see that its atomic number is 6. So this tells us that carbon contains 6 protons. And if we have a neutral carbon atom, then we also have 6 electrons. So now if we try to draw this electron diagram of an atom of carbon, we can show how the inner shell contains 2 electrons out of the 6. And then the outer shell will have the remaining 4. So when we talk about valence electrons, these are the electrons in the outermost shell. So for carbon, carbon has 4 valence electrons. Okay, so now let's see what the junior tutor said. Valence electrons are often defined as the number of electrons in the highest energy level of an atom or ion. To determine the number of valence electrons in carbon, we need to write its electron configuration. So this is another method of answering this question. Electron configuration is a notation that shows how electrons are distributed in an atom or ion or molecule's atomic orbitals or molecular orbitals respectively. There are several principles that govern how electrons occupy the orbitals. One of them is the Aufbau principle. This rule states that electrons occupy the available orbital with the lowest energy. In atoms, the pattern or order of occupying the orbitals is summarized by Madelung's rule, which is illustrated below. Okay, so they show how just an easy way of writing out electron configuration. And then as you go down the arrows, this is the order in which you would write out your electron configuration. Okay, so they found out that carbon has 6 electrons. And then they also showed that the electron configuration of a ground state carbon atom is 1s2, 2s2, 2p2. The highest energy level in a ground state carbon atom is 2. So in this energy level, there are 4 electrons, 2 from the 2s and 2 from 2p. Therefore, a carbon atom has 4 valence electrons. Yep. So this solution is correct. Okay, so question number 8. How many valence electrons are assigned to oxygen when determining the formal charge of the ionic compound sodium methoxide? Okay, so let's try to draw the structure for sodium methoxide. If we were to count out the total number of valence electrons, sodium has 1, oxygen has 6, carbon has 4, and hydrogen also has 1, but we multiply this by 3 since we have 3 hydrogen atoms in this compound. So now in total, we have 14 valence electrons. So now let's try to draw this structure. We know that sodium will have a positive charge since it gave one of its electrons to this compound here, which contains the oxygen. Oops. Just won't draw it in brackets. Bonded to the carbon with 3 hydrogens. And now let's count out how many electrons I've drawn so far. So we have 2 electrons in each bond, and we have a total of 5 bonds. So we have 10. So we need 4 more electrons, and the remaining 4 will go on our oxygen. Okay, so we can kind of draw the ionic bond like this. And we can also find out how we calculate formal charge by using the equation where formal charge is equal to the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. Okay, so now let's calculate the formal charge of oxygen. And it should be -1. But if we were to calculate it, the valence electrons in oxygen is 6. The number of non-bonding electrons, which are in the form of the lone pairs, is equal to 4. And there are 2 bonds to oxygen. So in total, we have 4 valence electrons divided by 2. So 6 minus 4 minus 2 would give us 0. But if this wasn't in the compound with the sodium, then we would only have two bonds, two bonding electrons to the oxygen. So that's why, and we'd also have this extra lone pair as well. And that's why before they come together, this is how it has its negative charge. So let's just show how this -1 is before our ionic bond with sodium, and then after bonding is what we did earlier, which is the 6 minus 4 minus 4 over 2, and then it becomes neutral. So this is after donating electrons to our sodium. Okay, so now let's see what the junior tutor said. Valence electrons are electrons on the outermost shell within an atom. These electrons are responsible for forming a bond with another atom, and oxygen belongs to group 16 in the periodic table, wherein all elements within this group have 6 valence electrons. Thus, when determining formal charge in the ionic compound sodium methoxide, 6 valence electrons are assigned to oxygen. Oh, so they only asked for valence electrons, so I just calculated formal charge just to show how we would do so. So this solution is correct. Okay, so now I believe we are on question number 9. Question 9. What is /R the spectator ions in this reaction? Okay, so we have HC2H3O2, which can also be written as acetic acid. So I'm just rearranging the atoms to make it easier to see it as acetic acid, which is aqueous, and it reacts with sodium hydroxide to form sodium acetate. So let me write it like this. Sodium acetate plus water. Okay, so this is our molecular formula. And typically, our next step would be to separate these substances into their ions if they were all aqueous and not in the solid or liquid phase. But if we look at our acetic acid, this is a weak acid. So this means it does not readily dissociate into its ions. And it only partially dissociates. So when we write out our ionic equation, our acetic acid will remain as an acid. So it's not going to separate into an acetate ion plus a proton. It's just going to remain as CH3, COOH, and then the rest of our substances will separate into ions. For example, sodium plus OH minus, and then we can have this produce sodium acetate, which will separate into its ions. And our water, since it's in liquid form, will also stay as is. So now this is our ionic equation. And when we write out our net ionic equation, this is when we would cross off any spectator ions that appear on both our reactant side and our product side. So in this case, it's sodium. And now we can write out our net equation, which is the acetic acid plus OH minus reduces the acetate ion plus water. Okay, so therefore our option is C. Okay, so now let's see what the junior tutor said. Steps to writing the net ionic equation. Step 1 is to write the balanced chemical equation. Step 2 is to write the state symbol for each substance. Step 3 is to split soluble compounds into ions. 4 is remove spectator ions by crossing them on both sides of the complete ionic equation. And then step 5, write the remaining substances as the net ionic equation. So our equation was already balanced. And then they showed that only the sodium hydroxide and the sodium acetate will separate into ions, making sodium plus the only spectator ion for this equation. So this solution is correct. Okay, so question number 10. What is the ground state electron configuration for each atom and ion pair? Okay, so first we have nickel, and then we have nickel 2 plus, B, we have manganese. Do it in a different color because it might get a bit crowded. B, we have manganese and manganese 4 plus. C, we have Y, which the name escapes me right now because it's not commonly used element. And D, Ta. Okay, so let's start off when we need to write the electron configurations for a certain atom or an ion. We first need to separate our periodic table into the different orbital shells. So for example, these first two columns is the S block, and this green part is the P block, and the middle transition metals is the D block, and the last two rows, which are the lactanides and actinides, is the F block. So then starting from hydrogen, we move left to right across the periodic table, writing the row number and then the block letter, and then we kind of just go in order of increasing energy levels. And then once we get to the D block, you'll notice that when we write the row number, it's going to be the row number -1. And similarly with the F block, it's going to be the row number -2. Okay, so let's start off with nickel, which is found right here. So its atomic number is 28. And then starting from the hydrogen, we write the row number, which is 1, and then the block letter, which is S. And then in the superscript, it tells us how many electrons are in that orbital. So we have 1s2, and then going on to the next row, we write 2s2, and then moving across to the p orbital, we're still in row 2, so 2p6, which is the electron configuration of neon. And then going down to the next row is 3s2, and then 3p6, and then now we're going to the fourth row, but in most cases we like to write in order of which energy level, like of increasing energy level. So instead of writing 4s2, I'm going to start off by writing 3d and then counting up to where our nickel is. So we have 1, 2, 3, 4, 5, 6, 7, 8, which brings us to the nickel. And then I'm just going to write 4s2. Okay, so these are kind of cut out. Let me just rewrite it. Okay, so this is the ground state electron configuration for nickel. So now let's see what happens if we were to remove 2 electrons. So now nickel has a positive 2 charge. So since 2 electrons got removed, they were removed from the 4s orbital. So now our new electron configuration looks the same, except the last two 4s2 electrons are now gone. Okay, so this is the electron configurations for nickel and nickel 2+. Now let's move on to the manganese. So again, we'll find it on the periodic table, which is somewhere. Okay, so we end up in 4s. Yeah, so it's right here. Atomic number 25. And we basically just need to do the same thing. So 1s2, 2s2, 2p6, 3s2, 3p6. And then again, I'm just going to write my 3d before my 4s. And if we were to count it, up to manganese, it's 1, 2, 3, 4, 5, 3d5, then 4s2. So then when we remove 4 electrons, then our new electron configuration becomes 1s2, 2s2, 2p6, 3s2, 3p6, and then 2 electrons from the 4s orbital are now gone, and then 2 more electrons from the 3d orbital are gone, so it becomes 3d3. Okay, so this is bugging me. I want to find out what the name of this element is. Yttrium. Cool. So it's found atomic number 39. And since it's pretty like down there, we can write the shorthand electron configuration instead. So when we write the shorthand electron configuration, we find the noble gas that comes before yttrium, which is krypton, and we just write it in square brackets. And then we just continue writing the remaining electron configuration. So for yttrium, I'm going to write the 5s2 first, and then 4s1. And then when we remove that last electron, it's just 5s2. So notice that this time I took an electron from the 4s orbital, and this is because, the 4d orbital. And this is because since there's only the 1 electron there, then it's most likely to just lose that electron than to take it from the 5s orbital. So this is just a reason why, like, sometimes with the transition metals, it can get kind of confusing. But typically, a partially filled d orbital is more stable than like when you just have a filled s orbital. So this is why for our other examples, we took from the d orbital instead of the we took from the s orbital instead of the d orbital. And now let's move on to our last element, Ta. Let's find it on this periodic table first. So this is called tantalum. So tantalum is found here. And again, let's write out the shorthand configuration for tantium. We would write xenon in square brackets. And then we would continue on to name the remaining we would go on to name the remaining electron configuration. So in this case, let's write out our 4f first. So also, the F block is inserted where this red line is. So we also have to take that into account when writing out our electron configuration. And since it's at a lower energy level than our 5d and our 6s, then we would write it first. So it goes 4f14, and this tantium is found here, so we need to write 5d3, and then finally 6s2. And if we were to remove the 2 electrons, Then our new electron configuration is xenon 4F14 5D3. Okay, so now let's see what the junior tutor said. The electronic configuration is composed of the principal quantum number together with the subshells sp, d, and f. And the superscript of the subshells are the number of total electrons in that shell. For this problem, the ground state electron configuration is the electron configuration of the natural state of the element. Meanwhile, the electron configuration of the ions affects the superscripts of the outermost subshell of the atom. So when you have a positive charge, this means electrons were lost, and when it's negative, this means they were gained. So now let's look at nickel. So ground state nickel has, the same electron configuration. And since the outermost shell here is the 4s, having 2 electrons removed will make the nickel ion change its electron configuration to end in just 3d8. And for manganese, they got the same thing. It will end in 3d3. And for this yttrium, I believe it's called. Yeah. When it loses the 1 electron, it loses it from the 4d1 orbital. So now it's just krypton 5s2. And then lastly, for this tantalum, it has the same electron configuration as xenon, and then 4f14, 5d3, 6s2, and then losing 2 electrons becomes 4f14, 5d3. Yep, so this solution is correct. Okay, question number 11. What is an Arrhenius acid? So there are different ways we can categorize acids. We can have Arrhenius acids, Lewis acids, or even Bronsted-Lowry acids. But by definition, an Arrhenius acid is when there is an increase in the concentration of protons in the aqueous solution. And I'm just going to add another point here that our protons can then react with water to form the hydronium ion, which is H3O+. So realistically, this is what happens in an acidic solution. So for example, if we had a solution with HBr, and water, this would look like H3O+, hydronium ions, plus Br-. So this is one way we can write out this reaction. But typically people like to only show HBr just on its own, which can dissociate to its ions, the proton plus Br minus. So both examples would be considered correct. The first one is it's a more accurate depiction of the reaction, but it's also like kind of more tedious to write H2O and then H3O plus. And sometimes it's just easier to just show HBr dissociating to the proton plus Br minus, but both would be considered correct. So now let's see what the junior tutor said. By definition, an Arrhenius acid is any chemical species that increases the number of protons or H plus ion concentration in an aqueous solution. Upon dissociation, these compounds form H plus or hydronium ions when combined with water. Some examples of Arrhenius acids are just like H plus in general, H3O plus, H2SO4. Yep, and then they just showed some examples there. So this solution is correct. Okay, so question number 12. Draw the Lewis structure of PF3 in the box at the right. There's no box, but we'll just draw it. And including the lone pairs. What is the molecular shape? The phosphorus fluorine bond is blank, so I'm guessing they're asking if it's like polar or nonpolar. The molecule is blank. And what is the bond angle? Okay, so when writing the Lewis structure, we first need to find out the total number of valence electrons in the molecule. So phosphorus has 5 valence electrons, and fluorine has 7. And since there are 3 fluorine atoms, we multiply this by 3. And if we were to add these up, we get a total of 26 valence electrons. So now I'm just going to draw my skeletal structure with phosphorus as my central atom, and then just the 3 single bonds to fluorine. And then I'm just also going to add in the lone pairs on my fluorine atoms as well. And if I count out how many electrons I've drawn so far, there are 2 bonding electrons in each bond, and we have 3 bonds. And each fluorine atom has 6 electrons that are in the form of lone pairs, so I only have 24 out of the 26. So for the remaining 2 electrons, I will put them on my phosphorus atom. So now we have the Lewis structure of phosphorus trifluoride. And now let's try to analyze its molecular shape. So if we focus on the central phosphorus atom, we'll see that it contains 1 lone pair, and it has 3 bonded atoms. So this is when we would use our VSEPR chart in order to help us answer this question. So when we have 1 lone pair and 3 bonded atoms, we have a trigonal pyramid molecular shape. trigonal pyramid molecular shape. And this also tells us that we have a tetrahedral electron geometry. And we also found out our bond angles, which were around 109.5 degrees. Okay, so that checks off some of our questions here. So let's find out, I think they want us to find out whether or not the phosphorus and fluorine bond is polar or nonpolar. So to answer that part of the question, we need to calculate difference in electronegativity between phosphorus and fluorine. So let's look up the electronegativity values. And fluorine has an electronegativity of 4. And phosphorus is 2.2. Okay, so now if we were to find out the difference in electronegativity, it would be 1.8. And I'll just write over here. Therefore, this bond is considered polar. And we know it's polar covalent because phosphorus and fluorine are two nonmetals. And also our difference in electronegativity is greater than 0.4. So this means it's not nonpolar, and we have a polar bond. I think they also wanted us to look at the overall molecule as well to see whether or not it was a polar or nonpolar molecule. And you'll see that all of the fluorine atoms, since they're much more electronegative than our phosphorus, this causes a net dipole moment going in the direction of the fluorines, and because of its trigonal pyramid molecular shape, this lone pair isn't able to balance out the electronegativity of the fluorines. So it's not a symmetrical molecule as well. So therefore we can say that PF3 is a polar molecule. And I'll just also say that the dipole moments don't cancel out. If we had, I'll just have an example. If we had our fluorines that were symmetrically arranged and there was no lone pairs like BF3, then this is considered a nonpolar molecule, even though it contains polar bonds. And you can see here that they're able to cancel each other out. But in our case, we have a polar molecule. And then we found the bond angle was around 109.5. So now let's see what the junior tutor said. List the elements, their valence electrons, and determine the total valence electrons. And they got 26. They drew out the skeletal structure and put the remaining electrons on our phosphorus, so they got the same Lewis structure as well. And then this is how they found out the shape by calculating the steric number of the central atom. This is the same thing we did as well, but they just refer to it as a steric number. So they counted out the number of bonded atoms, which is 3, and the number of lone pairs, which was 4. And they showed that it has a trigonal pyramid molecular geometry. So they have bond angles of 109.5, and since this molecule is asymmetric, it is a polar molecule. And then they determined the electronegativity difference of the phosphorus and the fluorine, and they found it to be around 1.79. So this is a polar bond. And we also know it's polar because it's between two nonmetals. So the solution is correct. Okay, so question number 13 is to give the full electron configuration for sulfur. Okay, so when writing out electron configurations, first we need to divide our periodic table, find it here, into different sections. So our first two rows is the S block, and then this green portion here is the P block. The middle transition metals is the D block. And finally, these last two rows, the lactanides and actinides, is the F block. And then we try to find sulfur on our periodic table. So it's right here, atomic number 16. And then starting from hydrogen, we move left to right across the periodic table, writing the row number and then the block letter. And then you'll notice that when we get to the D orbital, we write the row number -1. And when we get to the F block, we write the row number -2. So then let's start from hydrogen, and we write the row number, which is 1, the block letter, which is S, and then in the superscript, we show how many electrons are in that orbital. So there are 2 electrons in the 1s orbital. And then we move on to row number 2, 2s, another 2 electrons there. And then in the 2p orbital, it can house 6 electrons. And then moving on to the next row, we have 3s2. And then we get to 3p, which is where our sulfur is. And then we just count out 1, 2, 3, 4 electrons in this p orbital. And now this is the electron configuration of sulfur. And if we wanted to write the shorthand configuration, all we'd have to do is find the noble gas that comes before sulfur, which is neon, and we'd write it in square brackets, and then continue on writing the rest of the electron configuration as normal. So we write neon, and then 3s2, and 3p4. So this is also an accepted electron configuration for sulfur. Okay, so the junior tutor said that in writing the electron configuration of an element, we follow the Aufbau principle shown below, which states that the order of energy will dictate the order in which electrons are arranged in their orbitals. Therefore, the lowest energy will be occupied by electrons first. This is a simple way that we can also figure out the order of the electron configuration. Kind of write them all in the blocks like this, and then you go diagonally across and you get 1s, 2s, 2p, and then 3s, 3p, and then so on and so forth. Remember that each orbital can hold a different number of electrons. S orbital can hold a max of 2, the p can hold a max of 6, the d orbital can hold a max of 10, and the f orbital can hold a max of 14. And then they found the electron configuration to also be 1s2, 2s2, 2p6, 3s2, 3p4. So this solution is correct. Okay, so question 14 just asks, what is mass percentage? Mass percent can be written as an equation, which is the mass of your component that you're trying to find the mass percentage of. Component divided by your total mass of the mixture or the compound. So it just depends on what you're looking for, but this is why I'm just writing it in like simple terms. And then once you find that ratio, you multiply it by 100. And this is how you get the mass percentage of a component in a mixture or compound. So the junior tutor said that the mass percentage refers to the percentage of each element found by dividing the mass contribution of an element by its total molecular mass. Yep, so that's one way you can do it. Mathematically, you have the mass of the constituent element divided by the mass of the compound times 100%. Yep, so this solution is correct. And then question number 15. What is the ground state electron configuration of carbon? Okay, so let's first write out normally our electron configuration for carbon. We would need to first divide our periodic table into the different sections, the S block, the P block, the D block, and the F block. And then starting from hydrogen, we move left to right across the periodic table until we get to our carbon atom. And then we write the row number followed by the block letter and also show how many electrons are in that orbital in the form of superscripts. So let's start off by writing the electron configuration of carbon. We have 1s2, 2s2, and then 2p, and then counting up to the carbon, 2p2. So we should have 6 electrons in total. Since a neutral carbon atom contains 6 protons and also 6 electrons. But if we look at the options that are given in our multiple choice, you see they want us to specify all of the suborbitals or the subshells that are in 2p. So we can write out our electron filling diagram, just showing the different orbitals. So we can have 1s, 2s, and then these 3 will be referred to as 2p, but specifically they can be 2px, 2py, and 2pz. So now let's write out our electron configuration, actually showing where what the electrons would look like if they were in these different subshells. So for the 1s, it contains the 2 electrons. and they'll have opposite spins, like so. And we do the same thing for the 2s. Those two electrons have opposite spins. And then finally, when we get to the 2p, we would start off by just filling in the remaining 2 electrons spinning upward before we would pair, put them in the same orbital. So for example, like carbon only has the last 2 in the 2p, but if we had like 5, then the way that we would fill it up would be 1, 2, 3, and then you start to fill in the opposite spins. That doesn't really pertain to us. So now we can rewrite our electron configuration as 1s2, 2s2, and then specifically we have 2px1 and then 2py1. So if we look at the options, they give us, this is option C. And the junior tutor said the same thing. 1s2, 2s2, 2px1, 2py1. So this solution is correct. Okay, question number 16. Lead has a density of 300.2 whips per alfs if 1 gram is equivalent to 5.930 whips, and 1 milliliter is equivalent to 0.224 alfs. Determine the density of lead in grams per milliliter. Okay, so this is just a conversion question. So we start off with 300.2, and these units I've honestly never heard of. Whips over alfs. But we know the conversion factors. We know that 1 gram is equivalent to 5.93 whips. So when we convert whatever our desired grams, we want it to cancel out like our whips in this case. So since whips is in the numerator, if we multiply by the conversion factor, we now want it to be in the denominator so that it will cancel out. So we multiply it by 1 gram over 5.93 whips. And this will cancel out that unit. And then we also want to convert our alfs to milliliters. So now this is kind of the opposite. Our alf is in the denominator, and we want to get rid of it. So now we would put our conversion factor of 0.224 alfs in our numerator, just so that it can cancel out. And this is per 1 mil. So now we put milliliters at the bottom, since for our desired units, we want milliliters to be in the denominator. So if we divide 300.2 by 5.93 and then multiply by 0.224, we end up getting 11.34 grams per milliliter. And the junior tutor said the same thing. So this solution is correct. Okay, so question 17, is CO2 polar or nonpolar? If we were to draw out its Lewis structure, you'll see that it is a symmetrical molecule. And the carbon has no lone pairs. So we know that oxygen is much more electronegative, so we're going to have dipole moments pulling in the direction of the oxygens, but you can see that they cancel each other out. So therefore, CO2 is nonpolar. And it has 0 dipole moment, or net dipole moment. And the junior tutor said the same thing. They have the correct Lewis structure, and they noted that the molecular shape is linear, and since there is symmetry in shape and in the attached atoms, the molecule must be nonpolar. So this solution is correct. I think we have time for one more quick question. How many valence electrons does sulfur contain? So if we find the atomic number of sulfur, it has 16 protons. So since we have a neutral atom of sulfur, that means we also have 16 electrons. So if we try to draw out this atom of sulfur, it'll have 2 electrons in this innermost shell, and then 8 electrons in the next shell. So this is 10 electrons now, and we need 16. So then we just draw the remaining 6 in this valence shell. So then we can say that sulfur has 6 valence electrons. And the junior tutor said, electrons of an atom or element consist of 2 valence and core. So the valence occupies the highest energy level, or the outermost shell. So they drew out the electron configuration of sulfur. So this is another method of trying to figure out valence electrons. The highest energy level is n equals 3. And we have 2 subshells occupied with electrons on this energy level, 3s2 and 3p4. So they added up those subscripts and got 6 valence electrons. That's a different method as well, and it is also correct. Okay, so those are all the questions for today's session, and if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, you can leave it a like and a comment, and share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass. I hope to see you soon. Bye.